Alright, what's up guys? In this video, I'm going to pick up with some vector calculus here, and we're going to be talking about surface integrals. So as to evaluate this surface integral here, f of x comma y comma z ds, where f of x comma y comma z is equal to x minus y minus z, and s is the parametric surface given by r of u comma v is equal to u minus v, v minus u, and u minus 3v minus 1, where u is in between 0 and 2 and v is in between 0 and 3. Okay, so evaluating a surface integral on a parameterized surface it's not hard, but it's a relatively lengthy process, and I'm going to write down how we do it. Also, if you notice here, parameterized surface. If you notice here for our problem, they give us r of u comma v, which is our parametric surface. Don't expect that to always be the case with these surface integrals. Depending on what they give you as your surface, it could be an ellipse, it could be a cylinder, it could be a cone. You may have to find the parametric description of the surface on your own. In this particular case, they give it to us, but don't always expect it to be given to you, and you'll have to find it on your own. That typically can be found at the back of any calculus textbook. If your calculus textbook includes all 3 semesters, if you go to the back end where it's vector calculus, towards where the surface integrals are, there should be a section in that area that gives you the parametric description of certain surfaces, cones, cylinders, stuff like that. So I just wanted to mention that before moving forward. So basically, the formula is the surface integral f of x comma y comma z ds, and what it is it's the double integral. It's going to be f of x u comma v comma y of u comma v comma z u comma v, and then we're going to multiply all of that by the magnitude of the cross product of r sub u and r sub v, and then we'll have dA. So again, that's the formula. Again, it's not hard to remember, and like I said, nothing that really we need to do here is going to be hard, but it is quite lengthy. Okay, so if you notice here, we can go ahead and determine what our parametric equations are going to be for our parametric surface. So our first parametric equation is going to be x is equal to u minus v, y is going to be equal to v minus u, and then z is going to be equal to u minus 3v minus 1. Now what we need to find is r sub u. And remember, r sub u, that's just the partial of r with respect to u, which basically means that we just take the partial derivatives. So it'd be the partial of x with respect to u, comma, the partial of y with respect to u, comma, the partial of z with respect to u. That's what r sub u is. R sub v is basically this, the same thing, just with respect to another variable. So it'd be the partial of r with respect to v. And again, it'll just be the partial of x with respect to v, comma, the partial of y with respect to v, comma, the partial of z with respect to v. So I just wanted to clear up what r sub u and r sub v, what those were, and we'll basically go through and do everything. All right, so now that we got a bunch of the formulas and stuff out of the way, we can go ahead and actually start working on it. So the first thing that we need to do is to find f of r of u comma v. So remember, f for us was x minus y minus z, and so therefore we could say that f of r of u comma v, in our case, it's just going to end up being u minus v minus v minus u minus u minus 3v minus 1 We can simplify that a little bit. So we'll get f of r of u comma v. And if we simplify, well, it looks like we'll get u plus v plus 1. Now let's take our partial derivatives. So we need r sub u, so that's what we need. So what that really is just the partial with respect to u. And remember, it was u minus v, comma, v minus u, comma, u minus 3v minus 1. All we have to do is take the partial derivatives. And remember, when we're taking a partial derivative with respect to, in this particular case, with respect to u, that means we're treating the other variable as a constant, or we're holding it fixed, basically. So it looks like we'll get 1, negative 1, and another 1. So that's r sub u. Let's find r sub v. Okay, so this time it's the same thing except with respect to a different variable. So this time with respect to v. And again, it's the same thing. It's going to be u minus v, comma, v minus u, comma, u minus 3v minus 1. And let's go ahead and take our partial derivatives here. Let's see what we get. Okay, so in this case, it looks like we'll get negative 1, another positive 1, and then in this case, we'll get negative 3. So this is going to be r sub u, and this is going to be r sub v. Now, why do we need that? Because we have to compute the cross product. Because if you go back to our formula, we now need to compute this part. We'll compute the cross product of r sub u and r sub v, and then we'll find the magnitude of the cross product of r sub u and r sub v. So that's the first couple of things that we wanted to do to get that out of the way. Like I said, evaluating the surface integral on a parameterized surface, it's not hard, but it is lengthy. It takes a bit of time to kind of get through the problem. So just be aware of that. Let's go ahead and start with our cross product and kind of get that out of the way. So remember, for the cross product, we just use the matrix method. So we'll draw a little matrix here. The first row will be those unit vectors, I, j, and k. The second row will be when we took our partial derivatives. So it'll be 1, negative 1, positive 1. And then it'll be negative 1, positive 1, and negative 3. And hopefully you know how to compute the cross product. If you don't know how, I have videos on that, by the way. So we eliminate the first column and first row, or we eliminate the row and column containing our first unit vector, which is I. And what that does, and that leaves us with negative 1, positive 1, 1, and negative 3. Make sure you're being careful with your sign changes. Then it's to be minus, because remember, it's I minus j plus k. So keep that in mind. Same thing, we're going to cancel out the column and row containing j. And in that case, that just leaves us with 1, 1, negative 1, and negative 3. Then, put your j behind it. And then we'll add that to what we get when we cancel out the column and row containing k. So that'll be 1, negative 1, negative 1, and positive 1. And then we stick our k on the outside there. So that's how it should be set up. Now, the better you get at doing cross product, like if I were doing, I'm so good at cross product that if I were doing cross product in a class, I wouldn't even write out all this extra stuff. Because once you've gotten basically used to the process of calculating the cross product, the less steps you have to write. So you won't have to write all that stuff down, the better you get at it. But if you're just learning it for the first time, it is best that you write stuff down as much as possible until you get familiar with the process. And hopefully you're familiar with how to find determinants, because that is all we're going to do here. And we're going to get our cross product here of r sub u and r sub v. Okay, so it looks like what we're going to get here is, looks like we're going to get 2i plus 2j, and we'll get 0 for the last component. So we can just write r sub u and r sub v as 2i plus 2j. So that's the cross product there. Okay, so that takes care of that process. Now the next thing we need to do is to find the magnitude of the cross product of r sub u and r sub v. So that's just the square root of the sum of the components squared. So it's going to be what we're going to find next. So let's go ahead and get that out of the way. So that's going to be the square root of the sum of the components squared. So that's going to be the square root of 2 squared plus 2 squared, which gives us the square root of 8. If we do prime factorization, we can write the square root of 8 as 2 times the square root of 2. So we could say that the magnitude of the cross product of r sub u and r sub v is simply just going to be equal to 2 times the square root of 2 if we do some prime factorization. So now we have basically everything we need at this point to go ahead and evaluate the double integral now. Well, we pick the surface integral and evaluate it as a double integral. And remember, the difference between you can always have the difference between a surface integral and a double integral based off the differential. So remember, with a surface integral to be ds, for a double integral it would be dA. So you can always tell the difference between the two. So in our particular case, if we go back to the surface integral that we were given before, it was f of x comma y comma z ds. Now remember what f of x comma y comma z was, because we got to make sure we're subbing in everything correctly. And we know the limits of integration, and we're going to integrate this du dv. So that means that we'll have this integral on the outside here will be from 0 to 3, and then the innermost integral here will be from 0 to 2, because we're integrating it du dv. And you have to make sure that the integrals match up with the correct differentials. Make sure they match up properly so you get the right answer. And if we stick everything in, we'll get u plus v plus 1 multiplied by 2 times the square root of 2, and we'll integrate this du dv. Okay, so remember, for a double integral, we integrate, well in this case, we're integrating respect to u first, treating v as a constant, and then we'll integrate with respect to v last, and you work your way from the innermost integral to the outermost one. So the first thing that you should do is pull out 2 and pull out the square root of 2, because they're both constants, they're both just numbers. So we'll have 2 times the square root of 2. We'll pull that out, and then we'll have the integral from 0 to 2, and we'll just have u plus v plus 1, and this is integrated with respect to u. Okay, so this is really just the integral from 0 to 2. It's going to be u du plus the integral from 0 to 2, v du, plus the integral from 0 to 2, it's going to be 1 du. And those are relatively easy to calculate. So we got 2 times the square root of 2. And it looks like here, u, with respect to u from 0 to 2, that's going to give us 2. Remember, we're treating v as a constant, integrating it with respect to u, so that would be v times u from 0 to 2. And in that case, we'll just get 2v. And then over here, from 0 to 1, we're integrating a constant with respect to u, and obviously that's just going to give us a 2. So really what this is 2 times the square root of 2, essentially multiplied by 2v plus 4 if we simplify it. So this would be 2v plus 4 when we do the simplification. And now we move to our outermost integral and integrate that with respect to v. So it'll be the integral from 0 to 3. And what we'll have is 2 times the square root of 2 multiplied by 2v plus 4. And that's integrated with respect to v. So again, 2 times the square root of 2 is a constant. So we'll have 2 times the square root of 2. And then on the inside here, we'll have the integral from 0 to 3. We'll have 2v dv. And then it'll be plus the integral from 0 to 3, and it'll be 4 dv. Okay. And as we continue, we see what we get. So 2 times the square root of 2, we still got that. So we got the integral from 0 to 3 for 2v dv. Well, that's just going to be 2 times v squared over 2 from 0 to 3. And we see what we get for that. Okay, and this will be 4 dv, so in our case, we'll have 2 times v to the second all over 2. I guess I'll show you guys how to do this part. And then you just plug your stuff in. We'll get 9 over 2 minus 0, which will give us 9 over 2. Multiply that by 2. So we'll get 2 times 9 over 2. Well, 2 times 9 is 18. Divide that by 2, you get 9. So we'll get 9 for that. And then if we go over here, we're integrating this constant 4 with respect to v. So that would just be 4v from 0 to 3. And if we sub in this, we'll get 12 and subtract away 0. We're not taking anything away. And so in that case, it looks like what we're going to end up getting is 9 plus 12, which is 21. So we'll get 21 here. So this would be 2 times the square root of 2 times 21, which would just give me 42 times the square root of 2, which would be our answer. So your final answer for this surface integral on this parameterized surface is just going to end up being 42 times the square root of 2. And that would be your answer. So the answer is going to be 42 times the square root of 2. All right, so hopefully what we did wasn't too bad. Again, just a bit of a lengthy process for this type of problem. But by the time you get to this point, everything that we've done so far, or that we did throughout the problem, you will have been familiar, or should have been familiar with pretty much most of the process, and it's not hard to go through it at all. It's just a bit lengthy. I think sometimes people confuse lengthy problems with hard problems, and I don't think it's necessarily hard. I just think it's a bit lengthy. So that's going to be your answer. So let me know if you guys got any questions about it. I'll be more than happy to address it. I'll see y'all next time.